Hello everyone, I am Dr. Sirajul Faisi. I welcome you in my YouTube channel. Today in this video, I am going to talk about general elucidations of a structure of terpenoids. So I have already uploaded 3 videos on terpenoids. This is my 4th video. So let us start from here. Presence of oxygen atom. How you will confirm the presence of oxygen atom and especially presence of carbonyl group. Terpenoids containing carbonyl functions form crystalline addition product like oxime, phenylhydrazone and bisulfite. If carbonyl functions is in the form of aldehyde, it gives carboxylic acid on additions without loss of any carbon atom, whereas the ketone on oxidation yields a mixture of lesser number of carbon atoms. You can see reaction with NH2OH hydroxylamine, it gives an oxime. If you have phenylhydrazine, it gives phenylhydrazone. If you have sodium bisulfite, you will get this product, sodium disulfide product. So now presence of unsaturations. You know the unsaturations, meaning of unsaturation, presence of double bond. The presence of olefinic double bond is confirmed by means of bromine, and number of double bond determined by analysis of bromide or by quantitative hydrogenations or by titrations with monoperthalic acid. So presence of double bond also confirmed by means of catalytic hydrogenations or addition of halogen acids. Number of moles of HX absorbed by one molecule is equal to number of double bonds present. You can see here one double bond, take 2 hydrogen, catalytic hydrogenations, it gives the saturated product. Again you see unsaturations, double bond react with HX acid, it gave the saturated product. So addition of nitrosyl chloride NaCl, this is the Tilden's reagent. You can see additions of NO and Cl at adjacent carbon. This is the addition product. Epoxide formation with per acid. You see CH3, C, 3 oxygens and hydrogens, it gives the epoxide and acetic acid. Gives idea about the double bond present in terpenoid molecule. Now friend, dehydrogenations. Dehydrogenation give carbon skeleton. On dehydrogenation with sulfur, selenium, polonium or palladium, terpenoids convert to aromatic compounds. Examination of these products, the skeleton structure and position of side chain in the original terpenoids can be determined. For example, alpha terpenol on selenium dehydrogenation yield parathymine. You can see alpha terpenol is a terpenoid. It undergo dehydrogenations. It gives parathymine. So it indicates the parathymine structure, skeleton present in alpha terpenol. Now friend, dehydrogenations, thus the carbon skeleton of terpenol is as follows, like this. Now friend, next oxidative degradations. Oxidative degradations has been the parallel tool for elucidating the structure of terpenoids. Reagent for degradative oxidation are ozone, acid, neutral or alkaline potassium permanganate, bromic acid, sodium hypobromide, osmium tetroxide, nitric acid, lead tetraacetate, and peroxyacid. Since oxidizing agents are selective depending on a particular group to be oxidized, the oxidizing agent is chosen with the help of a structure of degradations product. So, number of the ring present, how many ring present, how you will find out. With the help of general formula of corresponding parent saturated hydrocarbon, just remember, number of ring present in that molecules can be determined. Relations between general formula of compound and type of compounds. You can see general formula of parent saturated hydrocarbons and type of structure. If you have CnH2n plus 2, acyclic, CnH2n monocyclic, CnH2n minus 2, bicyclic, CnH2n minus 4, tricyclic, CnH2n minus 6, tetracyclic. You can just remember formula and the structure for your objective questions. For example, limonene, molecular weight or molecular formula C10H16. Absorb 2 moles of hydrogen to give tetrahydrolimonene, molecular formula C10H20. Corresponding to the general formula CnH2n, means limonene has monocyclic structure. Now, friend, spectroscopic studies. You have learned spectroscopic studies in previous classes. All spectroscopic methods are very helpful for the confirmation of a structure of natural terpenoids and also a structure of degradations products. The various methods for elucidating the structure of terpenoids are UV spectroscopy, ultraviolet spectroscopy, infrared spectroscopy, nuclear magnetic resonance spectroscopy, mass spectroscopy, and X-ray analysis. Now friends, what is the UV spectroscopy? You have already learned in part 3 and previous semester 2 or semester 3. UV visible spectroscopy. In terpene containing conjugated dienes or alpha beta unsaturated ketones, UV spectroscopy is very useful tool for detections of conjugations. You know friend, the value of lambda max for various type of terpenoids have been calculated by applying Woodward's empirical rule. You have learned Woodward empirical rule. So parent system is butadiene, means basic and basic values. You see in basic acyclic diene, basic value 270 nanometer. Homoannular dienes 253 nanometer. Heteroannular diene 240 nanometer. Increment for each carbon substituents 5 nanometer. For exocyclic double bond 5 nanometer, and so on. So if you have the extended double bond, then 39 nanometer. So you can see isoprene, because this peak is present in your terpenoids. Isoprene lambda max 222 nanometer. So alpha beta unsaturated ketone means again basic value, and basic acyclic enone 250 nanometer. Increment for carbon substituent at alpha 10 nanometer, at beta 12 nanometer, at gamma 18 nanometer. Exocyclic double bond 5 nanometer. Extended conjugation 30 nanometer. So example, mycene acyclic diene 270 nanometer, carbon substituent 5 nanometer, total lambda max 222 nanometer. So friends, IR spectroscopy I will discuss in our next video. If you like this video, then subscribe my channel, and thanks for watching.